Bismillah, walhamdulillah, wassalatu wassalamu ala rasulillah. In this video, we want to learn how to apply the Laplace transform to perform circuit analysis and find solutions for the currents and the voltages. So we will be given a circuit, and this circuit will be given in time domain. And this circuit has basic circuit elements like resistors, inductors, and capacitors. What we will do is that we will apply a transformation that will take this circuit itself to the Laplace domain. And this can be done using the table shown. So what the table says is that every element can be changed by an equivalent model that represent its behavior in frequency domain. So for example, a resistor can be kept as it is. However, whenever you see an inductor, you can change this to either an inductor in series with a voltage source or an inductor in parallel with a current source. Now the value of the voltage source and the current source is determined by the initial condition I0, which represent the value of the current I0. I0 represent the value of the current right before time 0, or to be general, we can say right before T0 minus. T0 can be the time the switch moved, for example. And also we have to change, replace the inductor, the value of the inductor, by its impedance, and the impedance of the inductor is SL. Also for capacitors, same thing. We can replace the capacitor either by a voltage, an impedance in series with a voltage source, or an impedance in parallel with a current source. And for these impedances, the impedances is equal to 1 over SC for the capacitor, and again the value of the voltage source or the current source is determined by the initial conditions of the capacitor. And again, V0 is nothing but the value of the voltage across the capacitor at time V0 minus, at time 0 minus, or in general at T0 minus. That's just right before T0 minus. Now which model to use really depends on the circuit. Sometimes it's easier to use the series model, sometimes it's easier to use the parallel model. And of course, for the current sources and the voltage sources, you get to use the Laplace transform of the current sources and the voltage sources. So for example, if you have a current source and this current source has a value I, then you have to take this into the Laplace domain by applying the Laplace transformation, and same thing for the voltage source. Now this is the second step, and then we can do the circuit analysis exactly as we do the regular circuit analysis for circuits. We can apply all the circuit analysis techniques that we know, like the node voltage method, or the mesh current method, or the KVL or KCL, or whatever is that. Now once you apply the circuit analysis, you can find a solution for I and for V, the voltages and the currents that we want to find. But these values are in the Laplace domain. They are functions of S. So we want to apply one more step, which is the Laplace inverse transform. And by applying the Laplace inverse transform, we will get the solution for the current and the voltage, but in the time domain, not in the Laplace domain. Now what I will do next is that I will solve two examples. One of them will be in this video and the other one will be in a separate video. So this is now assessment problem 13.4 in Nelson, the 10th edition. It says the energy stored in the circuit shown is 0 at the time when the switch is closed. And it is assumed already that this switch was open for a long time so that the capacitor and the inductor is not charged by the 160 volts. So anyways, the initial voltages on the inductance and the inductor and the capacitor are equal to 0. And we are required in part A to find I in Laplace domain. So I don't have to worry now for the period t less than 0. For t less than 0, I have I0, which is the initial current of the through the inductor, is equal to 0, and V0 is the voltage across the current. So this is I0 is through the inductor, and V0 is across the capacitor. So V0 is equal to 0. Now the switch closed, so this is now for t more than 0, and when the switch closed, the circuit becomes like this. I have the voltage source in here, and then I have 4.8 ohm, 4 Henry, and this is 0.25 farad, and this is 160. Now this is the circuit after t equal to 0, but in time domain. The first step is to take this into the Laplace domain or the frequency domain. And usually I like in these circuits to use symbols instead of the values, because, well, sometimes dealing with these numbers, but for this case the numbers are pretty small, so I will just use them. So here I have 160 over S. This is the Laplace transform of the 160, because this is the same as so this is 160 now for t more than 0. So this is equal to 160 u of t. The Laplace transform of this is 160 over S. And then R, as we agreed, is equal to, will stay as it is. So this is the impedance of R, is equal to 4.8. And then for the inductor, the impedance should be LS, and L in this case is 4, so this is 4S. And for the capacitor, it should be 1 over SC, but C is equal to 0.25, so 1 over SC is equal to 1 over 0.25 C, and this is equal to 4 over S. So this is now my circuit in Laplace domain, and here is the current I. It's a pretty simple circuit. I have a voltage and I have a current, so the value of the current must be the voltage over the sum of the impedances. So I is simply the voltage 160 over S, and this is multiplied by the reciprocal of the sum of the impedances. So this is 4.8 plus 4S plus 4 over S. And I have S in here. I can distribute the multiplication over the addition, so I get 160 over 4s square plus 4.8s plus 4. And I need to simplify this further by taking 4 as a common factor. So if you take 4 as a common factor, then 160 over 4 is 40. So I get 40 in here. And then in the denominator, I have s square plus 4.8 over 4 is 1.2 s, and this should be plus 1. So this is now my I in the Laplace domain. So this is now the answer in Laplace domain, and this is the answer for part A. So this is part A. For part B, it says find the time domain expression for I when t is more than 0. So what I need to do now is to find the inverse Laplace transform of I of s. And there are many ways to find the inverse Laplace transform, but for this particular case, I think it's easiest to complete the square. And then I will use the formula that says that the Laplace transform of e to the minus at cosine omega t is simply omega over s plus a square plus omega square. So what I will do is that I will complete the square so that I have this form in the bottom. And completing the square means that I have to add half of the s coefficient squares. And this value is, well, half of 1.2 is 0.6. I need to add and subtract 0.6 square, which is equal to 0.36. So I have here 40 over, or I can also separate this into points, so because 1 is equal to 0.36 plus 0.64. So whether you add or subtract, or you just break the 1 into 0.36 plus 0.64 gives you the same answer. So I'll just use this thing in here. So this is s square plus 1.2 s plus 0.36 plus 0.64. So this can be reduced to 40 over, and here I have s plus a square plus 0.64. And well, a in this case is 0.6, because 0.6 square is equal to 0.36. So when you open this up, it will be s square plus 1.2 s plus 0.36, which is correct. And this 0.64, I will just rewrite this as 0.8 square. So omega now is equal to 0.8. Now the thing is that I need 0.8 up here. Up here I need 0.8, but I cannot just multiply by 0.8, so I need to divide by 0.8. So I just multiplied and divided by 0.8. So now the constant becomes 40 over 0.8, which is 50. So now I have 50. That's a constant. And then the rest, I have the fraction 0.8 s plus 0.6 square plus 0.8 square, and this matches exactly this form in here. So I will just apply the formula to get the inverse Laplace transform. So now I of t is equal to, I have e to the minus 0.6t, and this should be, oh, this is a sine, not a cosine, sorry for that. So sine, and then omega is equal to 0.8, so this is 0.8, and they have a constant of 50 here if we got the constant, and this 0.8 is multiplied by t, and the whole thing is multiplied by u of t, and of course don't forget the units. So this is now the answer for part B, which is the current in time domain. Next, in part C, it's asking that we find the S-domain expression for V now, and V is the voltage across the inductor from here to here, as shown. So the easiest way to find this is just to multiply I should have pointed here, so what I should do is that I multiply I, which is this current, by the impedance, and then I get the voltage from here to here, which is capital V. So I is this expression in here, so I will just multiply this by 4s. So now for part C, simply capital V is equal to 40. 40 times 4 is 160, so this is equal to 160s, and then the numerator I have s square plus 1.2s plus 1. And just for entertainment, I will find part D, which is asking for, and I should not forget the unit in here. The unit is volts, and the unit here is in amperes. So for part C, it's asking now to find the time domain expression for V, and just for the entertainment of it, I will just find the inverse Laplace transform in a different way now, which is by finding the roots of this equation here, so that you be exposed to both ways to do the inverse Laplace transform. So the first step is to factor this out, and to factor this out, I will find what we call the poles, which are the zeros of the denominator. So I'll just equate this 1.2s plus 1, I will equate this to 0 and find the poles. So using a calculator, P1 will equal to, I will find P1 and P2, and of course I know that P1 is equal to P2 conjugate, so only one of them is, I can find one of them, and the other one I can easily find by finding the conjugate. Now using your calculator, you will find that P1 is equal to minus 0.6 plus j.8. So this means that V will become, after factorization, 160s over, it should be s minus P1 times s minus P1 conjugate, or P2. So s minus p1 is s minus this, so I will revert the sign. So this is plus 0.6 minus j 0.8, and the other one should be s plus 0.6 plus j 0.8, and this is 160 s, and this can be broken to k over s plus 0.6 minus j 0.8 plus k conjugate over s plus 0.6 minus j 0.8, plus sign here. And now I want to find k and k conjugate. Well, finding k conjugate is not difficult if you have k, but to find k we will use the cover up method. So we will cover up this factor in here. This factor will be covered up. So what's going to be left is 160 s over s plus 0.6 plus j 0.8, and you want to evaluate this at s equal to minus 0.6 plus j 0.8. So you need to calculate this in polar form. If you use your calculator, you will find that this is 100, and the phase angle is simply 36.87 degrees. Now we can use the formula which says that the Laplace transform of k over s plus alpha minus j beta plus k conjugate s plus alpha plus j beta is nothing but twice the magnitude of k e to the minus alpha t cosine beta t plus theta, where theta is simply the phase angle of k. So k is a complex number that has a magnitude of k, and the phase angle theta. So applying this formula, we can reach that v is nothing but twice times the magnitude. This is the magnitude, so twice the magnitude is 200, and then e to the minus alpha in this case is 0.6, so this is 0.6 t, and then cosine the 0.8 is my beta t, and this is plus, and the phase angle in here is 36.87 degrees, and this is for t more than 0. You can either multiply this by u of t or write comma t more than 0, and the unit of course is in volts. So this is my answer for part C. It starts from, or part D, sorry. So this concludes my video. Wait for my other tutorial. Thanks for watching. سبحانك اللهم وبحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك.